Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all of you. So we will continue our class, which is in chapter 6. Chapter 6 is about power transmission, and we have divided the chapter into two subchapters, which is the belts and also gears. Chapter 6.1 is about belts. Okay, first of all, we need to know the method to transmit power or power transmission. We have a power drive, and we divided it into two: the flexible drive and also the direct drive. The flexible drive is for belt drive, chain drive, rope drive, while the direct drive is coming from gear drive and also cam drive. The belts, ropes, chains, and other similar elastic or flexible motion elements are used in conveying systems and in the transmission of power over comparatively long distance. So if we have a long distance to transmit power, normally we have the elastic or flexible type of drive. The use of these elements simplifies the design of a machine and substantially reduces the cost. These elements are elastic and usually quite long, so it is long. They play an important part in absorbing shock loads and in damping out and isolating the effects of vibration. This is the advantages of using flexible type of drive. Before that, we need to know the centrifugal and also centripetal forces. From Newton's third law, stated that force has a reaction of equal magnitude, the same magnitude, but in the opposite direction. A rotating body, as illustrated in figure 1.1, feels a centripetal. So we have the centripetal and also the centrifugal, where the centripetal force towards the center of rotation. So if the ball rotates counterclockwise, the centripetal force is going towards the radius, the center of rotation, while the reactive centrifugal, the opposite direction is the centrifugal force. So this one is centrifugal force, while the other one is the centripetal force, which going towards the center of rotation. The centripetal force is one that pulls the rotating mass. So we have a mass M, the rotating mass, towards the axis of rotation. So centripetal is going towards the axis of rotation. So the axis of rotation is this one. This is the axis of rotation. So the centripetal force pushes the mass towards the center of rotation. Take a mass M circling about a radius r at an angular speed. Its normal acceleration, pointing towards the center of the rotation, and the corresponding forces that act on the body can be described as, so we have the normal acceleration an as omega square r, omega square times r radius. Note that both centrifugal and centripetal forces have the same magnitude, but same magnitude, the same value, but opposite direction. So this is the direction of centrifugal force outwards the axis of rotation. So F is equals to MA equals to M times A. This one, we put it the normal acceleration to the equation. Okay, belts. Belts is the most flexible elements and do not have infinite life. No infinite life for belts. Characteristic of belts include they may be used for long center distance. Except for timing belts, there is some slip except for timing belts. So other belts, which is flat, round, and V belts, have some slip and creep. So except for timing belts. So timing belts don't have the slip and creep. And so the angular velocity ratio between the driving and driven shaft is neither constant nor exactly equal to the ratio of the pulley diameters. From the table, we can see that we have at least 4 types of belts. The first one is flat belts, round belts, V belts, and timing belts. Okay, so there is the figure of the belts, joint, size range for the belts, and center distance. This is examples of the flat belts. So the belts is flat, and we have driver, pulley, and also the driven pulley. Okay, so flat belts, we can see that the pulley is also flat. Okay, the pulley is also flat. So for the cross section, we can see that the belt is flat. Okay, just cut and look at the cross section for the flat belts. The round belts, so it is round if we cut the cross section, and that is the example of the round belts. V belts, if we cut the belts, this is something like V. Okay, but it is cut at the bottom. It's not like this one. Okay, so we cut that. V belts, timing belts. Timing belts, we have a pulley, either driver or driven, where pulley is like our gear. Okay, we have teeth, and timing belts also have the teeth, and we have also pitch from teeth to teeth. Okay, we have a pitch for the timing belts also. Flat belt geometry, as I said before, we have driver and driven gear. So the first one is the driver, and the second one is the driven by the driver. So this type is open belt type. Okay, so this is open belt type, and when the driver move clockwise direction, this one should be tight than the upper. This is the cross belt. So from the previous, if the belts move clockwise, the driver move clockwise direction, so do the driven move the clockwise direction. Okay, so the cross belts is the opposite of the open belt. The opposite, because the driver and driven is not the same direction. Okay, if we can look at our driver and also driven pulley, so the driver will rotate clockwise direction, so this one will go there. So this is the rotation of the driven counterclockwise. So then it will move. So we can see that the driver is in clockwise direction, while the driven is in counterclockwise direction. We use this if you want to have the opposite direction of rotation for our shaft. Okay. This is also the examples of the flat belts, open and also cross belts. Belt drives are either reversing or non-reversing. So it is we need to know the same direction, clockwise with clockwise or clockwise with counterclockwise. So as I show from the previous slides, okay, the shafts need not be at right angles as in a flat belt drive with out of plane pulleys. Okay, so this one is clockwise direction, this one is clockwise direction. While for this is non-reversing. Non-reversing means the driver and driven pulley is the same direction. So non-reversing. But for the cross belt, this one is clockwise direction while the driven is counterclockwise direction. That is reversing belt drive. The other one, if we want to have the opposite direction of the driven pulley, so we have, let's see this one, we have this one for counterclockwise number 3, clockwise direction, and then we have this one counterclockwise direction, going that one. So this one is counterclockwise direction. This one is counterclockwise direction. Okay, so 1 clockwise and 3 counterclockwise, and reversing but open belt because we don't have this one cross belt at any point of the system. Okay, reversing open belt. Okay, this is a quarter twist belt drive. An idler guide pulley must be used if motion is to be in both directions. So this is an example of the flat belts that we use, that we can change. This is our shaft for the driver or driven, and we have 90 degrees. So it is flexible, so it can be rotate in the other direction. So this drive, next one, this drive eliminates the need for a clutch. Flat belt can be shifted left or right by use a fork. So use this one to move to the left or to move to the right. Okay. This one also for variable speed belt drive. So we have the different size of pulley for driver and driven. It is some kind like of gearbox, so that we have different, or we can see it if we look at our bicycle, mountain bikes, we have front gear and rear gear. So this is some kind of different diameter, so that we have different speed for our bicycles. Okay. Modern flat belt drive consists of a strong elastic core surrounded by an elastomer. These drives have distinct advantages over gear drive or V-belt drives. A flat belt drive has an efficiency of about 98%, which is about the same as gear drive. On the other hand, the efficiency of a V-belt ranges about 70 to 96%. So for V-belts, 70 to 96, but for flat belts, 98. Flat belt drives produce very little noise, so noise reduce and absorb more torsional vibration. So absorb torsional vibration is increased from the system that either V-belts or gear drives. So flat belts is from this one, you can see that flat belts is better than the V-belts or gear drive. There are at least the advantages listed in the slides for belts, which is designed to sleep when overload occurs. So if we have V belts, we have belt drive. So sometimes there are loads bigger at the driven, so the driver cannot rotate, but the pulley still can rotate and the belt is slip. Okay, so if we have overload, the belt will slip. Resist abrasions, require no lubrication because no metal to metal contact. With smooth running, can transmit motion and power over long distance. So long distance is means very long, operate effectively, and it is versus the gear. Okay, if we have the gear, operate effectively at high speeds, flexible shaft center distance, inexpensive when compared to other drive where chain or gear. Okay, easy to assemble and install, have flexible tolerances, absorb shocks very well, and easy and inexpensive to maintain. If we look at our flat belt driver, so this is the equation for open belt drive. We have our diameter, small diameter, bigger diameter of the driven. Okay. So I try to show that we have okay. This is the we have driver and driven. So from the figure, I will show you how to determine the equation. Okay, so the equation from okay, so this is the line that parallel to the line here. So we have theta d, theta d. Okay, so bigger d and small d, capital D. Okay, so we look at the we call here as alpha here, or we call here as alpha. So that is the notation of alpha there. If we do the triangle, and we can have also alpha here. Okay, so from that alpha, and we have our line here as C. So we have C, and this one is the we know that the radius d and this is the same radius. Okay, this driver radius for driver. So we have here d over 2, and this one here is d minus d over 2. Okay, so from that one we have our triangle. This is C, this is alpha, and we call this one as an A, and here we have d minus d over 2. Okay, from that one, we know that alpha, okay, so from that one, sine alpha is equals to d minus d over 2, okay, divided by c. That is for the sine alpha. So we have, from that we have d minus d over 2c, and alpha is equals to sine negative d minus d over 2c. Okay, that is for alpha. So from that we have in radian we have also this one also alpha. So for theta d, bigger one, we can see that we have 180 degrees plus 1 alpha and 2 alpha. Okay, we have pi plus 2 alpha, while the driver is negative, minus 180 minus 2 alpha, which is pi minus 2 alpha. So that is the equation. So from that one, we know that alpha is this one. So the equation goes to pi plus 2 sine negative d minus d over 2. Okay, so this one, theta d is equals to pi plus 2 sine negative d over d minus d over 2c. See here. Okay, while the other one is pi minus 2 sine minus d over 2c. Okay, that is this one. So plus and minus. Okay, so we have another thing which is so the other one is our line. Okay, so from the previous figure, we have A, C, and also D minus D over 2. Right, so for a triangle, we have that C square is equals to A square plus D minus D square. Okay, then we have A square equals to C square minus D minus D over 2 square. Right. After that, we can take it out. C square minus 1 over 4. Okay, D square. Take it out. And then we have 4A square equals to 4C square minus D squared. Okay, so from a square we have 1 over 4 c square, sorry, 4c square minus d square. Then after that we have a equals to 1 over 2, and then the whole, this one is 4c square minus d square. Oh, sorry, wrong notation. Square. So this is the length. You can see here L is equals to 4c square minus d square square root. Okay, so this is the A, while we have another d theta d for this one and d theta d for this one. Okay, so that is our length of the belt. So this is how the equation for belt length. Okay, so if we have the cross belt, so we need to add some info, and it's the same from the triangle, and then we can calculate, and this is the equation for theta and L. Okay, we'll continue our mechanics of flat belt drives. From the free body of finitesimal element of a flat belt in contact with a pulley. So this is the belt. Okay, the centrifugal forces ds can be expressed as, so ds is centrifugal forces, so mr d theta r omega square, so this is fc d theta for centrifugal. Okay, so due to centrifugal force, so we get that ds equals to fc d theta. So for the equation A, when v is the belt speed, summing forces radially, so radial gives the summation of radial, we have divided that one, and also f. Okay, so for radial, going towards r is positive, so we have f df, f plus df d theta over 2, and we have also f times d theta over 2. Okay, so both of this one is on the negative direction, so this one is negative, dn is going on the r direction, same as also ds. So dn is positive, ds is positive. So we remove the higher order of this one, df. Okay, so we have negative f d theta over 2 minus f d theta over 2 plus dn plus ds equals to 0. Okay, so this one is equals to negative f d theta. So from that, we get that dn is equals to f d theta minus ds. So that is the equation B. Tangential. Okay, so for the tangent, we have F df and also F in the opposite direction, and we have also the friction. Okay, friction F dn with the same direction of F. So for tangent, we have three forces involved. F plus df. Okay, this is the first, minus F minus F friction df equals to 0. So from A and B, so from the equation of A, ds is equals to fc d theta, and also dn equals to f d theta minus ds. So from that one, we can solve it. For df is equals to f dn equals to f d theta minus f ds, and f d theta f ds. Okay, so this is our ds. So df over d theta is minus friction f equals to c. Right. So from that one, that is for the bulk. So the speed is pi dn over 1000. Omega equals to gamma b width and thickness. Gamma is the weight density, and hook tension centrifugal force equals to omega over g times v square speed. So we continue of the mechanics flatbed drive. So for the first one, for this one is the driver. So the tight side tension F1 and loose side tension. So this is the tight tension. This is the loose one. So F1 is the tight, F2 is loose. On the pulley, have the following additive component. So for the tight, okay, so the different for F1 we have the tight tension, tight side tension. F1 is equal, so this is for the initial tension. Fc is for the centrifugal. Delta F is the top, transmit top. Okay, so we debit as initial, centrifugal, and T over D, diameter of the pulley. So F1 and also F2, the difference is the notation of plus and minus. Okay, so we want to find our F1, Fy, Fc, F2. Okay. Alright, so from this one, okay, so from F1 and also from F2, if we take F1 minus F2, okay, we get 2T over D. Okay, so F1 is equals to Fi plus Fc plus T over D. Fi, Fc, T over D. F2 is to F initial, F centrifugal minus T over D. Okay, so this one F1 minus F2, finish, and this one is positive minus negative TD we got it T over D plus T over D. So we have 2 T over D. Okay, what else if we add our F1 and F2, we find that 2F1 is equals to, F1 plus F2 is equals to 2Fi plus 2Fc. Okay, so Fi is equals to, from this one, we come out with that one, Fi is equals to F1 plus F2 divided by 2 minus Fc. Okay, so we get our F1, Fi. So from this one, from I, we divide the Fi by T over D. Okay, so T over D. Okay, this one. Okay, so from that one, this is F1. Okay, so this is T over D. So we get T over D is equals to F1 minus F2 over 2. So this is T over D. Okay, so from that one we solve the equation. So finally we get this one. So we can see that there is the pattern, the same equation, but the difference is only for plus and minus. So this one we call it exponent F psi. Okay. So from that one, this is the same. This is plus and negative. So from that one, Fi, so K equals to Fi over T over D. So from that we bring T over D to this side, and then we get Fi is equals to T over D exponential F psi plus 1 exponential F psi minus 1. Okay, and we can do this one to get our F2. Okay, so that is our F2 after we solve the equation. And then we have torque, horsepower H, and also torque. This is the equation for horsepower and also our torque required. Okay, this is the correction factors, and this is the steps for flat belt analysis. Okay, so this is flat and round belt materials. Okay, so this is material, leather, polyamide, urethane. So there are specification. This is round urethane. Okay, and we have also the specific weight. Okay, and also we have also the coefficient of friction for each of the belts. Now we go for timing belts. A timing belt does not stretch appreciably or slip, and consequently transmits power at a constant angular velocity ratio. No initial tension is needed. Timing belts can operate over a very wide range of speeds, have efficiencies in the range of 97 to 99%, require no lubrication, and are quieter than chain drive. Okay, timing belt is some kind like gear. Okay, have a teeth and also have the pitch. Okay, so this is the pulley, or we say the pulley gear, and we have the root diameter, root and outside diameter. So the root diameter is this one. Okay, and outside diameter is this one. So teeth to teeth and root to root for the diameter. And we can look at the pitch diameter. Okay, the pitch diameter is the circle. The pitch diameter is larger than the outside diameter, greater than the diameter distance across the top lengths of the teeth. So the pitch diameter is larger than our outside diameter. And we have also the pitch diameter, okay, pitch diameter with the pitch line. So the line for our timing belt. And we have also a pitch, okay. Pitch is from crown to crown, or we can say that this one to this one. That is the distance of our pitch, okay, belt pitch. The 5 standard inches series pitches available are listed in the table below. We have extra light, light, heavy, extra heavy, and double extra heavy. So this is the designation or the keyword, and this is the pitch for each of the designation of the timing belts. Now we go for V belts. For V belts, the standard V belts. Okay, so from this figure, okay, this is kind of like V, and cut it here. The theta is 40 degree. Okay, so we have A and B, where this is the width and this is the thickness of the belt. So we have here the width and the thickness of our belt, and this is the name, or we call it the section of a V belt. Okay, and this is the minimum shift diameter. So this is diameter and horsepower. Okay, this is we can see that this is the belt section for V belt. So V belt, this is the section for V belt, and this is the circumference. Okay, and this is the length conversion to obtain the pitch length. Okay, so to obtain the pitch length, we need to add this number for each of the section. Belt length and center distance. So this is the pitch length and the center to center distance equation for our timing belts. Okay, so this is for the length and this is for the center to center distance. D is the pitch diameter of large shift, D, big D, and small d is the small shift. Okay. Horsepower delivered, we have the HA for the allowable power. This is the correction factor. Okay, K1 is correction factor, refer to table 17.13, and this one is the correction factor, refer to table 17.14. The allowable power can be near to H tab depending upon circumstances. Belt tension, so this is the belt tension F1 minus Fc, F2 minus Fc, so this is exponential of F psi. Okay, so from the previous, F2 minus Fc equals to exponential F psi. Okay, the design power is given by this is power, and this is the equation. Okay, the centrifugal force Fc, this is all the equation, and you need it from the table. Okay, this is the V belt tension. This is the horsepower rating of the standard V belts. So we have the section A, B, C, D, E, and we have this is the section, we have the diameter. Okay, and this is the speed. Okay, belt speed. This is a correction factor for K1. Okay, so factor for K1, and this is correction factor for K2 from the equation, and the nominal Ks. Okay, so Ks, so we have the nominal power, and Ks is the factor, service factor. So from the table, the belt section for KB and also KC, this is the section, and we have also our 3V, 5V, and also at V section. Okay, so this is the calculation of the belt tension. So this is the example. You can go through the examples. Okay, because I want to show you the other types of equation from the other books. Okay, so belt speed V equals to omega R. Okay, and omega is equals to that one VB, okay, by dN over 12. That is feet per minute. Okay, feet per minute. N is the number of revolution, number of revolution. A motor is rotating at 1750 revolution per minute. Clockwise, a 4.5 inch sheave is attached to the motor shaft and drives an 8 inch. So this is the driven on lathe. Determine the velocity on the driven shaft on the lathe and the belt speed. Okay. For the belt selection, okay, for 3V, 5V, and 8V, for the belt selection, we are referring to the speed, and also we are referring to the horsepower. So this is the given speed, RPM, and this is the horsepower that we are using. Okay. The common strategy for cross belt, open belt, or we call reverse, non-reversing. Okay, non-reversing. Okay, from the figure we can see that we use V belts and also flat belt. This is the available sheave pitch diameter, which is this is table 11.2. This is table 11.1. So the difference is for each section belts for 3V, 5V, and also 8V belts. So this is the sheave for the sheave. Okay, this is for the sheave, and this is for the length. Okay, right. To avoid back fatigue and vibration, the center distance should be D2 below. This is the center must be larger than D2 and smaller than 3 times D1 plus D2. Okay, driver and driven. This is the standard length where C is this one and B is this one. So we need to have our D and also L to get our B, and then we can get our length. Contact angles, I have touched this one before. We use the bigger D and smaller D, big D and small d. Okay, so for the angle of contact, this is the example. So we go for the example. A belt drive is used to transmit power from an electric motor to a compressor for a refrigerated truck. The compressor must still operate when the truck is parked and the engine is not running. The 10 HP is rated at 3550 RPM and the motor shaft is 5 inch. The compressor shaft has 7.5 inch diameter. Determine the appropriate industrial belt size, the operating speed of the compressor, belt size, operating speed, and the belt speed. Okay, so we have 3 things to consider to calculate. So for the belt size, we use from the graph. Okay, from the graph, we have, we don't have graph. All right. Okay, so for the 10 HP, 3550 RPM. Okay, so from the graph, 10 HP, 3550. Okay, so we use 3V. Okay, 3V type belts. So this is 10 HP and 3V. So sorry, 10 HP and 3550. Okay, so that one goes for 3V. Okay, 10 HP, 3550, 3V belt. So from the graph, calculate driver shift speed. So we need the velocity ratio. VR is equals to D2 shift 7.5 and diameter of the driver 5 inch, so we get 1.5. And then the speed, we have W omega 2 D2 equals to omega 1 D1. Okay, so from there, for the second shift, we just put the value and then we get the speed. Okay, from the speed we change it to radian per minute, and then we can calculate the speed. So the operating speed of the compressor is this one, and then the belt speed. So belt speed is from this one. V is equals to omega R. So R is D. V is equals to omega R is equals to D over 2. So just put in the equation. So we have D1 is equals to 5 and omega 1 is 22,305 radian per minute. To change it in inch per minute, and then we get divide by 12 to get the feet per minute. Okay, so that is the example number 1. Now we go to the second example. A belt drive is required to reduce the speed of an electric motor. So from that one we have 50 HP, 1725 RPM, and a grinding wheel speed of approximately 600 RPM. So from the figure, this one is 1725, this one is 600, sorry, this one is 1725, okay. The electric motor is rated at 1725 and 50 HP. So what type of belt? And the grinding wheel speed 600 is desired. So we need 600 RPM. Determine the appropriate belt size. First one is belt size. Second one is suitable shift diameters. Okay, so we need the diameters. So now we are looking at the type of belts. Okay, type of belt. So we have 1725 RPM with 50 HP. So we are going back to the graph. So we have 50 HP. So from that 50 HP, we have this line. Sorry. 50 HP, and then we have 1725. Okay, so 1725 is slightly below than 1750, so we get 5V. Okay, belts of 5V. So that is the belt for the motor. So we have 5V belt. Okay, so we need to determine the diameter of the shift, diameter. So we need to calculate. Okay, so we need to calculate from the 1725 RPM. So we have omega is equals to 2 pi n. Okay, so we have 2 pi times 1725 is equals to 10,838 RPM. Okay, so that is the speed, and we only need 600 revolution per minute for this one. Okay, for grinding wheel 600 is desired. So from the equation, omega is equals to 2 pi n. So we have 2 pi and the speed is 600 revolution per minute. So from the calculation we get 3770 revolution per minute. So omega 1 is equal to 10,838. Omega 2 is equals to 3770. A belt speed is optimal. So from the equation, V equals to omega R. omega d over 2. So we get d, okay, d is equals to 2v over omega. Okay, so d1 and omega 1. So we get that 2 times v divided by omega, and we have 9.96 inch. So we need to look at the 11.1 or 2, the table. Okay, table is 11. Okay, so what type of belt do we use? Which type? 3V, 5V, or 8V? So from the graph, we use 5V, right? For the 1725 RPM and also 50 HP. So 50 HP. So from the calculation, we calculate that the shift is 9.96. So 9.96 is around here. So we use 10.2. Okay, we use the bigger one, 10.2 for our shift. Okay, so from the table 11, we use 10.2 inch. So 10.2 is the D1. Okay, now from the same, V is equals to omega R. So we calculate that the speed is 4606 feet per minute. And then we need to find the driven. Okay, we need to find the driven. We have velocity ratio is equals to omega 1 omega 2. So from that we can calculate our velocity ratio. Velocity ratio is 2.87. Now from the velocity ratio, VR is equals to d2 over d1. Okay, WD. Okay, so the velocity ratio, we have d1 and then we have 2.87. Now we have 29.3 for the shift. Okay, 29.3. So 29.3. Now the process is 27.9. Okay. So we use 27.9 and then we calculate again our speed and we get 630 revolution per minute. So to calculate the belt, we use the equation and we get the length of the belt is 204.9 inch. Okay, so 204.9 inch for 5V. This one 204.9 inch. Okay, we use 212. We get 212 inch for the length. Okay, from the table we get we choose 212 and then we calculate and get, sorry, okay, this one is actually we need to calculate B first, and then from we get the value of B, then we put it in this equation, so we get C, and then we use C in this equation. Okay, use the equation and then we have. So you can calculate the exercise 1 HP, 600 RPM. So we need to find 3V, 5V, or 8V. Okay, a V belt drive is required, 250 RPM. Select the appropriate V belt and commercially available shift. So we need to find a shift, then determine the actual velocity of the driven shift and the belt speed. So V is equals to omega R, and then we have omega D1 equals to omega 2 D2. Okay, and then you need to calculate the L and also the C, so we can have the belt length of the belt that available in the market. Okay, so that's all for our belt, which is a flexible transmission power. That's all. I'll see you in the next subchapter, which is gears. Thank you very much.